This video is going to be on electrical properties. We're going to start off by talking about Ohm's Law. This is one reason we're talking about Ohm's Law is anytime you talk about electrical things in engineering, science, normally you do talk about Ohm's Law. Figure we'll touch on it here. The other reason is there might be some homework or other problems that it might be beneficial to have some of these numbers and equations. And so we'll go ahead and just start off with it. Ohm's law in one of its forms is V equals IR, voltage equals current times resistance. And so I have off to the side here the units. So voltage is joules per coulomb, current is coulombs per second, and so resistance is, if we just do a little bit of algebra, voltage per amp, which is also what current is measured in. And we could simplify that, or I guess even just break it apart a little bit more and say that resistance is joule seconds per coulomb squared, which is our ohm. Now, one thing that is interesting if you think about it, and maybe you have thought about this before, but maybe you haven't, is that Ohm's law seems to not care about the material. And so it's material independent. That doesn't make sense from anything that we've discussed so far in this class. Everything seems to really depend on the material that you choose. And so we'll talk about that briefly. Electrical resistivity, which we use our Greek letters here, is going to be R times A over L. Now, A here is not our current, it's not amps. What we have is, I will draw a quick picture. We're going to have a circuit. This is my voltage here. And if I zoom in on part of my picture here, this is my wire. This isn't like any type of electrical component or anything. I've just zoomed in here. This is my wire. A wire has this cross-sectional area. This here is my A. And my entire wire has some length to it as well. I am just going to talk about this zoomed in portion. I have some length L. And so what our resistivity is, it is our resistance times our cross-sectional area of whatever our electrons are flowing through, divided by the length of whatever it's flowing through. We could rearrange that a little bit, but what that really shows is that I have R, which is our resistance, which doesn't seem to be material dependent, but it actually is. And it's material dependent not only because of the dimensions, but because of our resistivity. Resistivity is going to be a material property of whatever our wire is made of. Electrical conductivity is basically the exact same thing, but it's just the inverse. So electrical conductivity is the inverse of the resistivity. All right, there's four main types of electrical materials. We have conductors, insulators, semiconductors, and superconductors. We're not talking about superconductors in this class, at least not in our lectures and our videos. If you want to read up on them, learn about them, that's perfectly fine. They're very, very interesting, and it might even be a good idea for your research paper or your research project at the end of the quarter. We'll talk first about conductors and insulators, and then we'll spend a majority of the time talking about semiconductors because those are the ones that are very, very interesting. What causes electrical properties? Well, the ability a material has to allow moving charges is really what we're looking at here. So if a material allows for charges to move very easily, we call it a conductor. If it does not allow for that to happen, we call it an insulator. And all these things are going to depend on the bonding. It's going to depend on the atom, the molecule that we're talking about. It's going to be determined by the microstructure. It's going to be determined by a whole lot of things. Just like we've been talking about previously, the bond, the crystal type, the material, everything is going to really come together and explain what's happening with these properties. And we're going to start with our energy. So we talked about this a long time ago. and you've done it in chemistry, I'm going to look at an energy diagram for one atom. So here's my energy. And I could have something here like a 1s energy level, and a little bit higher I have a 2s energy level. And that's what we have. And this is for one atom, and we could fill in the electrons that we have, and we could say, look, we have this energy level, everything's great, it makes sense. But what we want to do is we're talking about a lot of atoms here. What's happening when a lot of atoms bond together? So what I'm going to do is I'm going to redraw this, but this time instead of for one atom, I'm going to draw it for multiple atoms. I'm not going to draw it for a ton of them. I'm going to draw it for 4 atoms. And if I have 4 atoms, that means that I have 4 states. Even for each level here, for the 1s I have 4 states, for the 2s I have 4 states, and I'm going to kind of draw this as a function of the distance that my 4 atoms are away from each other. If they're really, really far apart, they're not interacting at all, and they act like they're not interacting. They just have their normal 1s state and their 2s state. But what's going to happen is as they get closer and closer together, they're going to start interacting more and more together with each other. And these states are going to start to split apart as they get closer and closer together. And the 2s is going to do the same thing. Now, depending on the material, depending on the atom, depending on the bond type and all those things, maybe these atoms won't get very close together, and maybe they will. We're not quite sure until we look a little bit deeper. But what we want to do here is we want to say, all right, so what happens if I have more than 4 atoms? Well, if I have more than 4 atoms, this is going to happen. They're going to split apart even more. They're going to interact even more the closer and closer they get to each other. So let's say that I look at a cross section here, a cross section right here. So I have this bottom, I'm going to call it a band, this bottom band of energy levels, and I have this top band of energy levels. So I want to draw exactly that picture. Here's my bottom band, and here's my top band. This is my energy. And let's say that right now, this bottom band is only half full or part full with electrons. That's what's going to be here. These are my electrons. Hopefully you can see that. That's just me writing my electrons inside of there. What I'm going to do is I'm going to call these my valence band. That's my bottom one here. And instead of writing valence band over and over, I'm just going to write VB. And the top one is my conduction band. Which I'm going to call CB. Now, if, let's say that I have these 2 bands, and again, that's what we're looking at up here. I have this bottom one, and I have this top one. And we're just saying for now that this bottom band is only half full of electrons. It means that there's still a need of some additional electrons somewhere. We would call this a conductor, and we'll talk about that in just a second. But what I want to do is I want to draw this one more time, because we have a different picture of our conductor as well, maybe a more common picture. I have my valence band, I have my conduction band, but in this case, they're overlapping. And that would be this picture if we were looking at a cross section, let's say a little bit closer. We can see that these bands are overlapping in this picture. That's the same thing that we have going on right here. So I have my bottom valence band, and let's say that this time it is actually all the way full of electrons. Both of these are pictures of conductors. And the reason we know this is because, remember, these are energy diagrams. This isn't a picture of what it looks like in 3 dimensions in space. These are energy diagrams. And so if we were to have some level of energy where at 0 Kelvin, where are all of our electrons sitting? What we're going to do is we're going to say that would be right here. And for now, I'm going to call that E subscript F. We'll talk about what that is in just a moment. But right now, that is just going to be kind of our, at 0 Kelvin, when we don't have extra thermal energy, no extra energy in our system, where our electrons sit. All of our electrons sit below that, no electrons sit above that. But if I do add just a small amount of energy, and it can be ever so small, what's going to happen is an electron can get promoted into this empty space. And in this picture on the right, an electron from the valence band can go to the conduction band. Once it's in that empty space, it is free to move. And the reason that it's free to move is because it's no longer at that low energy state. It's not just bound where it was at the very, very beginning. And how much energy do we have to add? Very, very little. Why? Because there's no gap between where our electrons sit and where we have an empty spot. So this is a picture of our conductors. Hopefully it's starting to make a little bit more sense. It should make a little bit more even as we move on and we talk about the opposite from conductors, as we talk about insulators. Then we can go back and we can say, all right, maybe I do see some where the similarities and the differences are. So conductors, this happens, this is basically what happens in metals here. We have this picture where we have this overlapping, and it's very, very easy to promote an electron into the conduction band. Once it's in the conduction band, that is a mobile electron, and we can move it around and we can get our conduction happening. All right, so let's talk about what an insulator looks like. Same picture. We have an energy level diagram. I have my 2 bands. I have my valence band. I have my conduction band. My valence band is going to be all the way full. My conduction band is going to be completely empty. So the question here is, what happens when I add just a tiny, tiny bit of energy? If I add a tiny, tiny bit of energy, I don't have enough energy for one of these electrons in the valence band to jump up to the conduction band. There's not enough energy to promote that electron. Okay, so I add a little bit more energy, and guess what? I still don't have enough energy to promote that electron. And so what this is actually an electrical insulator. I can't just push energy into here and say, hey, I want this electron that's sitting right here to hop up here. That's not going to happen because I don't have enough energy to do that. And a lot of times, if I do put enough energy in to do that, if I put enough thermal energy in there, I'm actually adding so much thermal energy that I'm going to actually burn the material before I actually promote any electrons into the conduction band. So insulators, it's very, very hard to promote an electron because I have a gap here. This is my band gap. And this band gap has an energy. Energy with a subscript G stands for my band gap energy. And for something to be considered an insulator, my band gap energy has to be greater than 2 or 3 electron volts. Now, I know that's not a hard and fast rule, but it really just depends on how much of an insulator you're looking at it, whatever the application happens to be. But if it has more than 2 or 3 electron volts of a band gap, we're going to call it an insulator. The reason for that is, again, this gap is too big for me to be able to push an electron from the valence band up to the conduction band. Semiconductor. Okay, so we have this idea of I have a conductor, very, very easy to promote an electron. I have an insulator here, very, very hard to promote an electron. A semiconductor is going to be somewhere in between that. It's not going to be super easy to promote an electron, but it's going to be doable. And the reason it's doable is because I have my valence band and I have my conduction band. My valence band, once again, is all the way full. And so if I want to promote an electron, if I give it a tiny bit of energy, nothing's going to happen. If I give it a little bit more, nothing's going to happen. But the band gap is close enough together, the band gap's small enough that I actually could promote an electron if I can add that amount of energy to the system, and the system won't burn before that happens. And so I still have this band gap here, but in this case my band gap is less than 2 or 3 electron volts. And again, it just depends on the property that I'm looking at. Sometimes it's very, very close to about 2 electron volts. Sometimes it's very, very small. It can just be a fraction of an electron volt. So that's our picture. I want to go through that one more time relatively quickly. All of our electrons have energy states, such as our 1s and our 2s states, and then we get into our p's and our d's and all that. When I put them together, when I have this ensemble of atoms that we put together and we call it a solid material, as those atoms get close together, they start to interact. When they start to interact, we get splitting of these energy levels. And that splitting creates energy bands. The bottom band that has electrons in it, we call our valence band. And then we have this upper band that's empty that we call the conduction band. If I can add just a tiny, tiny bit of energy and promote something into the conduction band, we call it an insulator. If I'd have to put a ton of energy in to promote an electron, we call it an insulator. And if I can put a little bit of energy in, nothing happens. But if I put enough in, but it doesn't have to be too much, kind of somewhere in between, we call that a semiconductor. Before we move on, I just want to really quickly add in, like we did from our conductors, our E sub f variable. I'm going to do that for my conductor as well. It's going to sit right in the middle of my band gap here. I want to be pretty quick on this next part. It's not super important for this class, but again, it is something that I think is important to mention. There might be some questions about the above energy diagrams. We'll talk about those in class. But one of those that I want to talk about now really briefly is what is E sub f. That is the Fermi energy. It's the energy corresponding to the highest filled state at 0 Kelvin. It's very easy to see here in the conductor. This is the energy of the highest filled state at 0 Kelvin, so no thermal energies in here, and that's the highest state that our electrons are at. Same thing for both pictures. That's the highest state. That description might fall apart a little bit when we look at our insulators and our semiconductors, because why then is it halfway up? Shouldn't our highest filled energy state be at the very top of our valence band for our semiconductor and our insulator? Which again is a good question. The reason for it is the way that we describe things. It's the math behind it. We use what's called the Fermi-Dirac statistics, or the Fermi-Dirac distribution. This is a probability of finding an electron since it's a probability, it ranges from 0 to 1. Like I said, I'm going to go through this pretty quick. I have an equation here where I can choose an energy. I have this Fermi energy, and I get some type of probability. I'm going to draw two quick graphs. So I have my energy here, and here I have my probability, 0, 1/2, and 1. That's my probability on this line, on this axis here. I'm going to have an energy up here that is my conduction band. All right, CB. Oof, that is a bad B. And I have an energy down here for my valence band. And somewhere right in the middle, I'm going to say that I have my Fermi energy. So if I plot this picture, or sorry, this graph, if I plot this equation onto this graph, what I'm going to get is something along these lines here, where at my Fermi energy, halfway between my valence band and my conduction band, I have a probability of 1/2. And again, that's the probability of finding an electron. All right, so if we look at this a little bit closer, and this is going to be a little bit important later, it's not the fact that we don't care about this at all. I'm actually going to plug in put a graph in here, and I'm going to put a couple different graphs in here. I have my Fermi energy, and my Fermi energy, it's always going to be halfway between. That's just the way that it works when I have my probabilities. If I'm at 0 Kelvin, so I'm going to plot a blue line for if I'm at 0 Kelvin. There is a 0% chance of finding an electron before my Fermi energy, and there is a 100% chance that I'm going to find it below my Fermi energy. And I'm just going to put a dotted line here to connect these two, but really nothing's happening in between here. Now let's say that I get something a little bit warmer. I'm going to do green here. I get something a little bit warmer. Let's say this is at about 300 Kelvin or so. Getting something too high up is almost 0. And so I end up kind of with this S-shaped curve again, similar curve that we have up here, but it's starting to bend out a little bit. So let's say that this green one is at 300 Kelvin. Let's say this blue one was at 0 Kelvin. And then let's say that we heat it up quite a bit. The more that we heat it up, the more probability we will find an electron that has been promoted. We have the thermal energy to do that. These are not good curves, so I do apologize. Let's say that this is at 800 Kelvin. What we're looking at here is we're looking at a probability. What's the probability that's happening? At 0 Kelvin, there is a 0 possibility of finding something above my Fermi energy, and a 100% chance that I find it below my Fermi energy. At 300 Kelvin, there is some probability that I'll find something below or above, and there's some probability I'll find it below. And so the same idea applies, but we find out that it can be temperature dependent, and that's the part that's going to be interesting, or that we're going to have to talk about as we move forward. So we've talked about conductors, we've talked about insulators, we've introduced semiconductors, briefly talked about what the Fermi energy is. Now we're going to jump back to semiconductors, and we're going to spend some more time, actually about the rest of the time in this video, talking specifically about semiconductors. All right, so semiconductor is, I'll go ahead and jump to our periodic table. A lot of times things in this column 14 are going to be our semiconductors. The one that works the best natural semiconductor that we use, that we know, is silicon. It's right underneath carbon. And because it's underneath carbon, it acts like carbon. It has the same structure as carbon, at least I guess I should say the similar structure as carbon. It has 4 valence electrons. And so I wrote out silicon's electronic structure here. It has 14 electrons, and we can divide them up as such. And we have these last couple shells here, this last shell here that is not filled. This is our valence shell, or our valence electrons. Getting back to hybridization theory, we could say if I have my energy here, I'm just going to sketch this out really quickly. I have my my 3s, I have my 3p's. If we didn't hybridize this, I would have 2 electrons in my 2s, and 2 of them in my 3p, and that would only allow me to have 2 bonds here. And we want to have a material, and we want it to act similar to carbon in a 3-dimensional structure, a diamond type structure. And so what we're going to do is we're going to hybridize this. This is going to be sp3 hybridize. And so we end up with this energy level where they all get split apart equally, and I can put an electron, 1 electron in each of those. That means that I get 4 bonds. Very important, 4 bonds. All right, so silicon is an intrinsic semiconductor. It means it's natural. In its natural state, it acts as a semiconductor. And the reason for this is silicon has its 4 bonds, has 4 electrons, and what it's going to do, it's going to bond to other silicon atoms. And we end up getting this 3-dimensional shape. If I add a little bit of thermal energy, some of these electrons that are in these bonds, and if I have this a potential, if I go ahead and try to push some more electrons in here, I put a voltage on here, what's going to happen is some of these electrons are actually going to become mobile. What's going to happen is this silicon has an electron, and this silicon up here has an electron. But as I push electrons through this material, as I try to have conduction go through here, a different electron could come and basically sit in this silicon atom, and it would bond. But what I could do is it could delocalize, and it could move to this silicon atom to the right, and a new electron would sit on the silicon atom on the left. And slowly I can go ahead and promote these electrons through. And it does take a little bit of energy for this to happen. The idea is the majority of the bonds in this silicon atom, or sorry, in this silicon crystal, are going to act like covalent bonds, but some of them are going to act semi-metallic. They're going to delocalize, and they're going to allow them to be delocalized a little bit, and that's dependent on the probability, again, back up here, the probability that I'm able to promote an electron into that conduction band. Once it's in that conduction band, it is able to delocalize and move somewhat freely throughout my material. So that's an intrinsic semiconductor, a natural semiconductor. What we want to do is we want to talk about extrinsic. Extrinsic semiconductor is man-made. It's something that we make ourselves, and we make it by doping. When I dope something, or when something gets doped, what we do is we add something to it that shouldn't be there. And when we add it to improve the properties. And so you've probably heard of doping in regards to sporting events. If somebody dopes, what they do is they add something to their blood, they add something to their body to give them an edge. This is no different whatsoever. We have silicon. We're going to make sure that we use silicon. We do have our silicon lattice. This is a picture of an intrinsic semiconductor. To make it intrinsic, what I'm going to do is I'm going to remove a silicon atom. I'm going to just do the middle one for now. And I'm going to replace it with something else. There are two types of extrinsic semiconductors. There's an N-type, and that's what we'll talk about first. What that means is it means that we're going to make sure that we have a higher charge than 4 in here. Remember, silicon has 4 bonds, and so the silicon atom in the middle here had 4 electrons. And so if I want to increase the charge, if I want to make sure that there's an additional negative charge in there, what I need to do is I need to put an atom in here that has more than 4 electrons. If we go back to P table, column 15 here, all of these have 5 valence electrons. And so I can use one of these atoms to dope our silicon. So what I'm going to do is I'm going to choose phosphorus. That was just to the right of silicon. And phosphorus has 5 valence electrons. 4 of them are used to bond to the neighboring silicons. And there's 1 left, and that one just kind of hangs out. What we've done here is we have made sure that we have an extra negative charge here, and this extra negative charge will allow, it's not bound to anything, which means that it is already mobile. I don't even need to add any heat or anything along those lines. I have this mobile electron already. It's just sitting here. Now, it is important to note that just because I add phosphorus to this and it comes with another electron, it doesn't necessarily mean that an N-type semiconductor is negatively charged. It's still a neutral charged material, and the reason for that is because the number of protons in the material matches the total number of electrons in the material. But what it does say is N-type just means that we have a negative charge that is allowed to move. So what we want to do is we want to give more negative. We can do that, like I said, by adding phosphorus or something else. We call this that we say that it has an electron donor, or that it is doped electron rich. We could do the same thing, and we could have a p-type. A p-type would be the exact same thing. I have silicon. But if I remove the middle atom and I add something that only has 3 electrons in it, boron. Boron, again, if we just peek at P table really quick, is just to the left column, column 13 here. So there are 3 valence electrons. Which means that it can only make 3 bonds, which means that one of these silicon atoms, we'll go ahead and say this one up here, it has this electron that wants to bond, but boron doesn't have the ability to do that. We say that boron has a hole. This hole is basically an anti-negative charge. It's not a negative charge, but yet there should be a negative charge there because silicon lattice says that there should be 4 bonds and we're missing an electron here. Because of that, we have a hole. We say that this is an electron acceptor or that it is hole rich. Both of these, p-type and n-type, both are semiconductors. One works by having extra negatives, and one works by having extra positives, or they look like positives because there should be a negative there and there's nothing there. So again, a p-type is a neutrally charged crystal. It's just the fact that we have less than 4 charges around here, around this boron, which means that we have a positive charge, or essentially a positive charge that is mobile. Really, the p-type and the n-type are just telling us what's mobile. Either the negative charge is mobile, or in the p case, the positive type is mobile. So I just have a little bit of information here. I think it's pretty much the same. I'm just going to read through it really quick. A hole is the absence of where an electron should be. It is, in essence, a positive charge. Remember that these are doped. So this is something that's important. Remember that these are doped crystals, doped materials. That means that the number of silicon atoms are still much, much higher than the doped atoms that we put into them. So the majority of this material is still silicon. I've just sprinkled in a tiny bit of boron or phosphorus. And that's an important thing because what this means is that the semiconductor, the overall crystal, retains the silicon lattice structure. It still wants to only have 4 bonds. It has the structure of silicon. If I were to put too much boron in or too much phosphorus in, it would change the actual structure of the material and it wouldn't act as a semiconductor anymore. It's very, very important that the P atom, the phosphorus, is sitting in a silicon site in a silicon lattice, and the same goes for the boron, that it's sitting in a silicon site in a silicon lattice. And this is the reason why we can't get that 5th bond for phosphorus, and we can't change our structure so that boron is happy and content and the whole crystal structure is happy and content with a 3-bond structure. If we were to get phosphorus to bond that 5th electron, then we wouldn't be able to have that extra charge be mobile for us. All right, so it is important to note that the electron and the hole both carry a charge. We call both of those charge carriers. One thing I think I did not put up here, I want to put this up here just so that you have it. This is our intrinsic semiconductor, our natural semiconductor of silicon. I just wanted to put that the band gap for this is approximately 1.1 electron volts. So that does fall within our range of being considered a semiconductor. As we dope things, what we're doing is we're tuning that. It allows us to change the value of our band gap so that we can get the band gap that we want. All right, so I want to draw a quick picture here about how both the electron and the hole carry a charge. We have our conduction band. We have our valence band. And our valence band is filled with electrons. But what I can do is if I can promote one of these, so this would be like pure silicon, an intrinsic semiconductor. If I can promote an electron, what happens is as I promote an electron, this electron goes up to the conduction band and it leaves a hole behind. I now have 2 things that are charged here. I have my negatively charged electron in my conduction band, and in my valence band I have a lack of a negative charge, or what we call a hole. Both of these carry a charge. So every time I promote 1 electron in my intrinsic semiconductor, I actually get 2 charge carriers. Now what if I have my extrinsic? Okay, that's supposed to say extrinsic. I apologize for that. It's a little sloppy there. If I have my extrinsic, I can have my valence band full of electrons. And what we've done is when we add extra, so let's say this is our N-type. When I add in our phosphorus, what I've done is I've sprinkled in some extra negative charge, and they're already in the conduction band before I add any heat or do anything to promote them. I just automatically already have some negative in my conduction band. I could then promote an electron as well. Leaving behind a hole, but you'd see that in this case, I have way more negative charges than holes or positive charges. So what we want to look at here is we want to jump way back to what we talked about at the beginning. We talked about Ohm's Law, and we broke Ohm's Law down into our resistivity and our conductivity. And we want to talk about what those are. So if I scroll up to the top really quickly, we have Ohm's Law that uses resistance. We said that resistance actually is has resistivity in it, which is a material property. And so we're going to talk about what that material property, kind of how to calculate it and what it is composed of. So our material property of conductivity, or the inverse resistivity, is dependent on three things. The number of charge carriers, and charge carriers are my electrons or my holes, so how many electrons or holes I have. The charge of the charge carrier, so it's an electron, so that's just the charge of an electron, and then mu, which is my mobility, how easy it is for that thing to move. For intrinsic materials, our N equals our P. Our negative charge equals our positive charge, and we see that in this picture above here. Every time I promote a negative charge carrier, I leave behind a hole, and so for every negative, I have a positive as well. For extrinsic, this is not the case, and we see that in the picture over here. For my N-type, I have much, much more N's than I have P's, or I have many, many more electrons than I have of holes. P-type is the opposite. I have more holes than I have of N's. We talked about temperature. We did that when we talked about Fermi Dirac. I'll scroll up to that really quick just to remind you guys. We have the probability of being able to find one of the electrons that have been promoted or not. That had something to do with temperature. We saw how temperature changed that, how we could promote our electrons that way. And so the question here is, what role does temperature truly play? Our conductivity is a function of temperature, and that is because two of my three things inside my conductivity are dependent on temperature. The charge, the fundamental charge of an electron, is not dependent on temperature. It's going to be consistent no matter what temperature we're at. But N, the number of charge carriers that I have, is going to be dependent on temperature. I can promote more of them as temperature increases, and my mobility is also dependent on temperature, how easily something moves. If I excite it by adding more thermal energy, they're going to move faster and they're going to be more mobile. All right, so let's draw a quick diagram here. For my N, I have what is happening in a conductor. In a conductor, I have this picture here, where at 0 Kelvin, this is the picture that I have. Everything is below my Fermi energy. if I'm not at 0 Kelvin? I do get some promotion. I have some charge carriers that have been promoted. So what happens? The higher the temperature, the more charge carriers that I have that can be promoted, the more conduction I can have into the conduction band. For a semiconductor, I have the same picture, but remember I have a gap that I have to overcome. So this one is at 0 Kelvin, and this one is going to be at not 0 Kelvin. So again, I have my Fermi energy right in the middle. And at 0 Kelvin, you can see that I don't have anything promoted, and temperature will promote things when things get hotter. So actually, heat is a okay thing, to a point at least, when I'm talking about semiconductors. The other thing that uses mobility, or sorry, that uses temperature or is dependent on temperature is my mobility. My electrons are going to scatter. And what are they going to scatter with? What are they going to run into? And by scatter, that's what I mean. They're going to collide with certain things. They're going to collide with one of two things. Number one, they're going to collide with other carriers. And by carriers, I'm talking about other charges. So electrons will bump into other electrons. Or two, they're going to scatter. They're going to bump into the lattice. There are, as they move around, there are essentially these positive cores of these atoms, kind of like these ions that are sitting there, that are going to interact with it as well. We need to balance these things out. We have a picture here of what is going on. I do the log of my mobility and the log of my temperature. And this is something, again, we're touching on this relatively quickly. If this is something that interests you, I would go ahead and just Google the mobility in semiconductors. Talk about lattice scattering or charge carrier scattering, impurity scattering. So here's the picture. I'm going to have impurity scattering or the carrier scattering. And I'm also going to have lattice scattering. And we'll see that as temperature increases, that one of these goes up and one of them goes down. The lattice scattering is going to actually go down as temperature increases because it's moving faster. We've given it more energy, and so that electron, that charge carrier, is moving really, really quick. It's not going to interact with the lattice as much. But as we increase our temperature, we are adding more and more charge carriers into this conduction band. It's like adding more and more cars onto the freeway. There are more things for it to interact with, so that conduction band starts getting full of other electrons, and it's harder and harder for them to move because they're interacting more and more with each other. And so we end up kind of having, as temperature increases, our mobility increases for a bit, but at a certain point our mobility starts to go down because we just get too many charge carriers that are moving. And that's one reason why there is a certain temperature that computers like to run at, and if we get them too hot, they don't work very well. One other thing that I wanted to mention real quick would just be drift velocity of an electron. The idea of drift velocity is how quickly, or the velocity of an electron. The electron actually doesn't move in a straight line. So the electron might bounce around a little bit. And so it's actually traveling much, much faster. But what we care about is how fast it basically goes from one end of the wire to the other end of the wire, and that's our drift velocity. When in reality, it's bouncing around, it's scattering, it's speeding up, it's slowing down, it's doing a whole lot of things in the process, but our drift velocity basically is how fast are our electrons moving through our wire. All right, so I wanted to just briefly talk about some applications for our extrinsic semiconductors, again, our N and our P types. And I'm going to talk about these relatively quickly. There's a good video online that you can search for and you can watch, and there are lots of good videos, but I'm going to tell you one that I enjoy, and it's more entertaining than listening to me for another 5 or 10 minutes, and so I will encourage you guys to look up that video. One thing that you can do with N and P type semiconductors is you can make a diode. A diode is an electrical component which allows current flow in only one direction. And so you do this by, we get some N type and some P type and put them next to each other. And what's going to happen is in the middle here, we're going to get what's called our depletion layer. What the depletion layer is, well, our N type has extra negative charges and our P type has these holes that could fill up they could fill with an electron, and so right there at where they meet, some of these extra negative charges, let's say that phosphorus brings, are going to hop over, and those electrons are going to sit in the holes that, let's say, boron brings, and this middle area here, our depletion layer, everything's happy. Everything has 4 bonds and no extra electrons sitting around. So there's no ability for additional electrons to fill the holes that are left over on the far right side because they can't get through this neutrally charged layer. So this is due to electron diffusion. Electrons from an N type diffuse to the B type. This creates neutrally charged depletion layer. Electrons can't get through the depletion layer without some electron potential in a specific direction. And so what we can do is we can actually force some type of flow. And so what we have is we have what's called forward bias. And so if I have an N and a P type, there's some depletion layer here. I put a positive charge on one end and a negative charge on the other. I can actually start to apply a little bit of voltage here, and it will clean up this depletion layer a little bit, and it will allow electrons to get into my P type, and then my electrons can continue to move. If we put it this way, if we have a forward bias, we get current flow. The other one is reverse bias. Reverse bias is where I just change. I put my positive on one side and my negative on the other side this time. This is hooked up reverse. It's like putting a battery in backwards. It's reverse. If I do this, there is no flow. And so this is how we can make something that is only going to have current flow in one direction. So there are some good things we can do just with a simple diode. What we could do, though, is we could make something even cooler. We could make a transistor. And a transistor are two diodes that are back to back. And so I could have an N-type material, a P-type material, and then another N-type material. So here we have a P-type semiconductor sandwiched between two N-types. I can have my positive and my negative. We call this the source and the drain. And what I have here is I have a transistor. A transistor can work as a switch or an amplifier. I need one more component here, and what we do is we put a gate up here. And it doesn't necessarily have to be an N-type, P-type, N-type. I could have one that is a P-type, N-type, P-type. You can set this up however you like. Again, you're the designer, you're the engineer. You can figure out what works for you. That's as far as I'm going to go. We could talk about how the transistor works a little bit more, what the source does, what the gate does, what the drain does. But what I would do is watch something that's a little bit more exciting than me talking about this. There's a video from the YouTube Veritasium, and it's called How Does a Transistor Work? So you can go ahead, jump on YouTube, look up How Does a Transistor Work by the channel Veritasium. Much more entertaining. It's nice and condensed. I think it's like a 5-minute video. Now that you have a little bit of background, watching that should make this whole section make a little bit more sense as well.